This video is the first of several videos about inputs and outputs. In the study of transforms and systems modeling, it's very easy to get wrapped up in the somewhat complex and confusing mathematics and lose sight of what each of these mathematical things means in the real world. To try and help prevent that, I'm going to be giving you lots of examples when we look at inputs and outputs. As we work through this part of the class, I encourage you to pay attention in your daily life to the things around you and see if you can identify inputs and outputs of systems and what kinds of signals they are. In this video, I'm going to be focusing on different kinds of inputs. We're going to look at each different kind of input mathematically, graphically, that is, how the input looks on a graph, and also in real life, what kinds of actual systems that you encounter every day have that kind of an input. There really are only 4 types of inputs that are of most concern to us. I'll list those 4 types of inputs here, and then we'll look at each one in turn. The 4 types of inputs are the impulse, second, the step input, third, a ramp input, and fourth is the sinusoid. Let's take a look at each of these individually. First, we'll start with the impulse input. For each of these different kinds of inputs, we're going to start by looking at what the input looks like on a graph. And the graph will always have time on the x-axis. Remember that we learned that a signal is a quantity that changes over time. And on the y-axis, this is the input. Now remember that the input signal is whatever you decide it is. That is, it's whatever quantity you're interested in modeling. It could be a force or a position or a current or a voltage. Whatever kind of input you're using for your system at the time, that input could be an impulse input. And if so, it would look like this. An impulse input is 0 at all times except for one time, usually at time 0, but not always at time 0. Now, theoretically, the amount of time that the input is non-zero with an impulse is actually 0 time. But of course, in real life, we can't have a non-zero input over 0 amount of time. The input would be non-zero for some finite amount of time. In reality, an actual impulse input is some large value over some short amount of time. Mathematically, the impulse function is written as delta, the Greek letter delta, as a function of t. And we would refer to this function as the Dirac delta function. If you want to find out more about this, go ahead and do a Google search on Dirac delta, and you can learn all kinds of fascinating things about the delta function. The Laplace transform of an impulse function is the number 1. Now I know that you don't know yet what is meant by Laplace transform, but I want to tell you what the Laplace transform is of each of these input functions so that you can start to try and notice patterns as we go. If you try and notice patterns now, it will be easier for you later on when we try to remember what the Laplace transform is and what it means. For now, I'd like to try and make the connection between this kind of an impulse input and what we would see in real life when we have an impulse input to a system. An impulse function is any kind of quick, high magnitude signal. For example, the clapper striking a bell is an example of an impulse input. In this case, the input is the force exerted by the clapper on the side of the bell, and the output is the motion of the material of the bell. When the clapper strikes the bell, it exerts an impulse input. The output in this case is a sinusoid, which we'll be looking at in a moment. Many other musical devices also use the impulse input in order to work. Striking the head of a drum, a hammer striking the strings of a piano, or a mallet striking the keys of a xylophone. These are all examples of systems that convert an impulse input into a sinusoidal output. Next, let's take a look at the step input. Just as before, we're going to start out by drawing a plot. The x-axis is going to be time, and the y-axis will be the input. In a step input, the input is 0 anytime that time is less than 0, and then the input jumps to a value usually 1 and continues 1 for the rest of time. For the step input, the value of the function f of t is equal to 0 when time is less than 0, and the function is equal to a when time is greater than or equal to 0. The Laplace transform of a step input is a over s if the value of the step input is a. Sometimes we'll use the terminology a unit step input. When we use the term a unit step input, it means that instead of being equal to some value a, the function is equal to 1 anytime that t is greater than or equal to 0. Let's take a look at some step inputs in the real world. One common application in the real world of a step input is flooring it. When someone in a car all of a sudden presses the accelerator down to a specified position, say all the way down to the floor, this is a step input. The input here is the position of the accelerator. The position of the accelerator is moved from 0 to a position. In our mathematical graph, it was shown as position A, and it is held in that position. If we know the transfer function of these cars, we could predict the output, that is, the velocity or the positions of the cars over time, given the input of a suddenly increased step input. Other examples of step inputs are a switch suddenly being thrown open, or a valve suddenly being turned from the closed position to the on position. The third type of input we're looking at today is the ramp input. We'll start by drawing the plot of time versus the input. A ramp input starts at 0 when time is equal to 0, and the value of the input increases at a constant rate over time. If the input value here is position, then we would say that the velocity would be equal to a constant equal to the slope of the ramp input. If the input quantity was, say, velocity, we would say that the acceleration would be constant. In a ramp input, the function f of t is equal to 0 when t is less than 0. And the function is equal to some constant a times time for any value where time is greater than or equal to 0. The Laplace transform of a ramp function is a over s squared. Now, let's take a look at some real-life examples of a ramp input. This video demonstration of the controls on a radio actually show different kinds of inputs, both step inputs and ramp inputs. Can you guess which of the buttons and dials on a stereo are step inputs and which are ramp inputs? Any of these buttons that you can press and release are step inputs. They turn a switch open or closed all at once when you press them. The volume dial, on the other hand, is a ramp input. When you take the dial in your hand and you turn it at a constant speed from a low volume to a high volume or the other way around, you are providing a ramp input to your stereo's circuitry. In this case, the output is the vibrations of the speaker, while the input is the current or the voltage provided as a result of your manipulation of the controls. Another example of a ramp input is the way that most people drive when a stoplight turns green. Typically, we don't floor it like in the videos I showed previously. We generally accelerate at a slow and constant rate. This is a ramp input. As we move the accelerator slowly at a relatively constant rate from its starting position to where we stop, we're giving the car a ramp input. Lastly, let's take a look at the sinusoidal input. A sinusoidal input in a time versus input magnitude plot starts at 0 and has some constant amplitude and some constant frequency. Mathematically, we write the sinusoidal input like this. F of t is equal to 0 when time is less than 0. And f of t is equal to an amplitude A times the sine of some frequency omega times t when t is greater than or equal to 0. The Laplace transform of this function probably doesn't look like it follows the patterns that the other ones did. That's okay, we'll learn about why this is the case later on when we get to the Laplace transform section. The Laplace transform of a sinusoidal function is a omega over s squared plus omega squared. Don't worry about remembering these or understanding where it comes from right now. I just want to get you familiar with the kinds of terminology that we have in a transfer function. Later on, we'll go through in detail how we got these equations and what they mean. For now, let's take a look at some real examples of a sinusoidal input. We've all experienced sinusoidal inputs and the power of the kinds of output it can produce by swinging on a swing set. When you swing on a swing set, the motion of your legs and arms approximate a sinusoidal input. The effect of this sinusoidal input is something that we refer to as resonance. We'll be talking about that more as we go into looking at the different kinds of outputs. In this video, we looked at the 4 common types of inputs: the impulse input, the step input, the ramp input, and the sinusoidal input, which should actually be number 4, not number 5 here. There are other types of inputs. In fact, there are an infinite number of different kinds of inputs that you could possibly construct. But as it turns out, all other inputs other than these 4 can be produced by a combination of these 4. We'll be looking at that within a few videos from now when we look at something called the Fourier series. For now, these 4 types of inputs will get you pretty far in terms of understanding how systems behave and how we can use that to our advantage in systems modeling.